Hey guys, so let's go ahead and take a look at the equations we're going to need to use to figure out the volumes of the shapes on the backside of your paper. The first one we have is the right circular cone, and we're going to solve our volume here. These are just kind of crappy screenshots taken from Google, but it's the best thing we have since we don't have a textbook. So here we go. This one is pi times the radius squared times the height divided by 3. And let's look at it compared to the right rectangular pyramid below. This is length times width times height divided by 3. And they look a little bit similar, but I'm actually telling you they're virtually the same thing if you think about them in a slightly different way. Let's go ahead and ask this question. The base of the cone is what? It's a circle. And what is the area? What's the equation for the area of a circle? You might take a look back over here and see that it is hiding in my equation in pi r squared. That's the area of my base. The next question I have is, what is the area of the base of my rectangular pyramid? And you can see down here I have length and width, and so if you multiply length times width, you get the area of our base there. And so what do we have there? Built into our equation, length times width. And so what I'm trying to show you guys is this, that our equations both just have the area of our base times the height, and then finally it's divided by 3. Your final answer, your final step would be to divide it by 3. And this turns out to be the exact same thing for both different shapes. And there's a good reason for that, and let me show you right here. Can I bring that to the front? Okay, so I have brought this little picture in, and it shows inscribed shapes in a circle. And the first shape is our classic triangle. And just to make sure you understand, inscribed means it's a shape that fits perfectly inside of a circle. So our first one, yeah, our triangle there. Then our our square. This is a hexagon, 6 sides. And then finally this one, it looks like maybe it's an octagon. No, it's a decagon. It has 10 sides. And the point in showing you guys this is a little preview, a preview into calculus. The point of it is to say that the more sides you have in a shape, in a regular shape, regular means they have all the same equal sides, the closer it's going to be to a circle. And so here I have a triangle with 3 sides. With 4 sides, you can see that my circle still has a lot more area than my square, but the square takes up more area than the triangle does. The hexagon takes up more area than the square did, and then if you look at this decagon, it's getting really close to the shape of a circle. Imagine what's going to happen when we go and have a shape with 20 sides, or maybe 50 or 100, or even 1,000, or even 1,000,000 sides. Now, by the time you get to 1,000 sides, the shape in red is going to be virtually the same as the circle it's inscribed in. And this is a little preview to limits, and it tells us what happens when we really push the numbers of things up higher, and we can see kind of where formulas come from in some of these cases. So enough of that. This idea is going to come back in the next couple of pages as well, so you can look forward to that. Okay, so again, just to review this one real quickly, the area of our base times the height will give you the volume of a right circular cone or a rectangular pyramid. There we go. So these are what are called inscribed shapes. The first one is my inscribed triangle in a circle, and inscribed just means it's inside of it, and it also, the corners touch the circle. So I have an inscribed triangle, an inscribed square, an inscribed hexagon, and then as an octagon. Yeah, no, it's not an octagon. It's a 1, 2, 3, 4, 5. It's a decagon. But the point of this is that if you add more sides to a shape, it slowly becomes closer and closer to a circle. And so this has 3 sides, so it's obviously not filling up all the space there. 4 sides gets a little bit more. 5 sides definitely more. And once you get to 10 sides, you can see, wow, this thing is really starting to fill up my circle. It's becoming more and more similar to my circle. And you can imagine what would happen if I had some sort of shape with 100 sides, or 1,000 sides, or even 1,000,000 sides. At that point, you wouldn't be able to tell the difference between that shape, 1,000,000 gone, and a circle. They would look identical. You'd need a microscope, and it wouldn't never. It's essentially a circle. So go back to this. Okay, the next shapes we're going to tackle are going to be the right cylinder and the right rectangular prism. And just in case you guys missed it already, those last formulas should definitely be in your notes. You're definitely going to need them again coming up soon. So make sure you're copying all this stuff down, please. Okay, so we have a similar situation. We have the right cylinder and right rectangular prism, which can be grouped together again. How do we think about that? It's because we have, again, a circular base with its little equation snuck into the volume formula. And it's multiplied by the height. If you look at the right rectangular prism, we got length and width, width and length. They're kind of separated. They wrote this one differently. I usually write it length times width times height, but because of the properties we've learned before, we know that we can switch the order of things because of the commutative property. I could have length times width times height, or height times length times width. It doesn't matter the order. But anyways, the point is that width times length are snuck into my equation, and it's just multiplied by the height. Okay, and so really these again are the same thing. It's the area of our base times the height. The area of our base times the height is going to give us the volume of our shape. And that's right, once again, the same reason as before. These are similar because as we take more and more sides to a shape, it becomes closer and closer to a circle. And really a circle could just be thought of as a shape that has an infinite number of sides. Or if you don't like the word infinite, you could say 1,000,000 sides or 1,000 sides even. That gets you close enough. And so really they have the same exact equations when you think about it in terms of the area of their base times the height. Okay, last one, it's the volume of a sphere. This one is a little bit less, it's not common to any of the other ones really. It has, it still has circle, the area of a circle built into it sort of in pi r squared, but we've added another dimension to that. Our radius is now cubed. Don't mess that up. A lot of you guys might be tempted to put in pi r squared here, and that will give you an error. Don't forget also PEMDAS rules, like always. We need to take care of our exponents first, so whatever our radius is, we're going to cube that. You can use your calculator's button for that, of course, or just do it by hand, but who likes to do that? No, I don't. So r cubed times pi, and then times 4 divided by 3 will give you what you need. And don't forget, for everything we've gone over today, we're going to have all of our answers in cubed form, okay? Because we're dealing with volume. Volume's always going to give us something to the third power. Okay, our units to the third power. So it could be centimeters cubed or feet cubed. They don't talk about this much, but you could have miles cubed or cubic miles. You can say cubic first. It doesn't really matter. And that's going to wrap it up.